Hello, and welcome to the next video in my series on basic statistics. Now just a reminder, these videos are geared towards individuals who are relatively new to stats, or for those who just want to brush up on basic statistical concepts. So that's being said, let's go ahead and dive right in. In this video, we're going to be talking about the difference between population data and sample data and how they are related. So a lot of the students I work with, they kind of understand what a population is and they know what a sample is, but aren't quite sure how they relate to each other conceptually. So we're going to begin a discussion of all of those things. So let's go ahead and get going. Now, like all my videos, I start with an introductory problem or scenario, and this one is fictional, and here's how it goes. We have a company named Halogen Incorporated, and they produce consumer-level compact fluorescent light bulbs, or CFL bulbs, as you can see over there on the right, for use in homes. Now, like any bulb manufacturer, Halogen tests its bulbs for longevity and power consumption. So they want to make sure that their bulbs are doing okay, so they test them, which should make sense. Now, Halogen expects its standard CFL bulb to last 10,000 hours and consume, on average, 20 watts of electricity. So we have some benchmarks there. Now, Halogen also claims standard deviations of 1,300 hours and 3 watts, respectively. Now, we have standard deviations in our data because, not every bulb is going to last exactly 10,000 hours. Some may last 10,500. Others may last 9,000. Others may last 11,000. But we're talking about, on average, 10,000. So the standard deviation just takes into account the performance of different bulbs. And the same thing goes true for the electricity consumption. Not everyone will consume exactly 20 watts of electricity. There's going to be some variation in their power consumption. Now, these figures are based on industry standards for all CFL bulbs. Now, the quality control manager needs to test whether or not Halogen's bulbs meet these standards. The initial production run will consist of 20,000 bulbs, and it is assumed that those 20,000 bulbs follow the industry standards outlined above. So, Halogen wants to test whether or not their 20,000 bulbs meet the industry standards of 10,000 hours of longevity and 20 watts of power consumption. Halogen cannot test all 20,000 bulbs, right? They're going to have some way of testing a sample of them. So we're going to consider our 20,000 bulbs our population, and then the test bulbs will be our sample. So let's go ahead and talk about those two concepts next. Population data. Now, oftentimes we need to ask questions about and collect data for an entire group or class or type of people or objects. Okay, an entire group. The key word there is entire. Say, the height for all women in the U.S. ages 18 to 35. Our example, the longevity in hours of all 20-watt CFL bulbs in our production run. The educational attainment of all frequent Starbucks customers. And the weekly time spent online in hours by all children ages 11 to 17. Now you can see there I've highlighted in the text the word all, and in the way I was speaking the word all. Because when we're talking about a population, we mean all members of that group as we define it. Now, the population itself is defined by the researcher. There are no set rules to apply when defining a population, except knowledge, common sense, and judgment. So you cannot define a population using two things that are mutually exclusive. So the height for all women would not include men. And we'll talk about that more here in a minute. So just common sense, knowledge, and judgment. Now, as you can see, populations can become quite large, We have 20,000 bulbs. In the case of all women ages 18 to 35 in the U.S., we're talking millions of people. So populations can be very large. Now, rarely can we collect data on all members of a population. It's way too much time and way too much expense. I mean, could you imagine trying to go out and measure the height of millions of women? It's just not practical. Even in conception, it's not even practical to think about. So there's no way to actually ever do that. But we still need to be able to make conclusions about the entire population. So, if we're a market researcher for Starbucks, and we are interested in the educational attainment of our frequent customers, say they come to the store 5 or more times during a given month, we want to make a conclusion about all those people for our market research, but there's no way we can collect data on all of them. So we have to come up with a way around that. Now, there is a middle ground here I just want to mention. When we do collect data from or about every member of the population, we call it a census. And of course, you're probably familiar with the U.S. Census. So every 10 years, U.S. Census workers go out and collect a tremendous amount of data on the U.S. population that is used for all kinds of purposes. But it's only done every 10 years. Well, why is that? Because, well, people don't want to be bothered every year, but also because it costs a lot of money, and it takes a lot of time to do. So that's why it's done so infrequently. But it is a very large slice of the population that's included in it, relatively speaking. Okay, let's talk about sample data. When we need to make a conclusion or an estimate about an entire population, we almost always use a sample or multiple samples from our population of interest. So in our light bulb example, we're going to test a certain number of bulbs out of the 20,000 to make our conclusions and estimates about the entire population of 20,000. But we're only going to use a sample. Now, a small but well-chosen sample, that's very important, a well-chosen sample can accurately reflect the characteristics of the entire population from which it is chosen. So in our light bulb example, we're going to choose randomly. Now, if we have 2 machines that are making bulbs, we'll do random samples on both machines because there could be a difference between the 2 machines. If we want to find the average height of women 18 to 35 in the U.S., we're going to take a sample of women, maybe in different geographical areas, women of all that age range, 18 to 35, and so forth. So you can see how the well-chosen part of this point is very important. Now, a few things to keep in mind. All elements or members of a sample must also by definition be part of the population as it is defined. Now, I will give you a couple examples in the next slide about how these things can be violated, but for now, let's go ahead and mention them. The sample should be representative of the population from which it is drawn. In almost all cases, if not all cases, samples from the same population should be independent of each other. That's a more complex idea, and I'll try to clarify it in the next slide. Now, in many cases, the sample is chosen randomly from the population. We call that a random sample. However, there are other methods for doing samples, but for now we're going to focus on the random sample. Now, on the last slide I mentioned several guidelines or ideas you need to follow, but here are some ways in which those can be violated. So I call these our sample selection no-nos. Now, I'm going to use the height for all women in the U.S., ages 18 to 35, as our example. Let's look at our first guideline. All elements in the sample must also, by definition, be part of the population as it is defined. So how is our population defined above? Well, the height for all women in the U.S., ages 18 to 35. So we're talking about height, we're talking about only women, we're talking about only women in the U.S., and then only women in the U.S. ages 18 to 35. So that is the boundary of our population. Now, there are other women of different ages. There are women in different countries, of course, but we are defining our population as it is stated above. Now, how can we violate that? Well, if the sample includes men, that's obviously going to violate this guideline. If we include women that are below 18 or above 35, even though they do exist, that is going to violate the way in which we defined our population above. Okay, and there are other ways. We could include women from another country. That would violate our population as it's defined at the top there. Look at the second guideline. The sample should be representative of the population from which it is drawn. Now, how can we violate that? Well, let's say half the sample consists of women who are playing in the WNBA basketball league. So how does that violate our guideline of it being representative of the population? Well, if half of our sample consists of women in the WNBA, it's going to skew our data. And why is that? Well, it's because women in the WNBA are on average significantly taller than the average woman aged 18 to 35 in the U.S. If it consists of such a large portion, in this case half of our sample is going to be tainted. So we need to make sure our sample is representative of the larger population. Now, look at the third one. In almost all cases, if not all cases, samples from the same population should be independent of each other. Now, this one, again, is kind of hard to define, so I'm just going to try to do my best to describe to you what this means. Let's say we're recruiting subjects for our study, and as part of our recruitment push, we incentivize someone who agrees to join up for our study, and they refer a friend of theirs to also be in our study. And of course, maybe that friend then refers a friend of theirs. Well, what we tend to know is that our friends and acquaintances tend to be very similar to us, whether it's our age, our background, things like that. So we have a self-selecting sample because individuals all throughout are selecting people that are relatively like they are. In that case, the selection really isn't, each person isn't independent of the other person. They're actually related in some way, and that could skew our results. The second point here, it depends on the research study. It just depends on how it's being framed, but disallowing membership in multiple samples. So maybe I'm a presidential pollster and I call someone's house and I ask them, who they plan on, if they plan on voting and who they plan on voting for in the current presidential election. But a question on my survey is, have you been contacted before by another polling company? And if they answer yes, then I do not use their survey. That means that our data isn't really, quote, random, is it? Because we are disallowing certain people because they've already been asked the same question. Maybe we're an entirely different company. But what happens is the total number of people being surveyed sort of changes. So that's a more complicated one to think about. But depending on the study, sometimes, the same measurement is not allowed to be included in a second or multiple samples. So of the four, that's the one I'm least worried about you understanding at this point, but it is, independence is an important part of many studies and many samples. Okay, last one. In many cases, the sample is chosen randomly from the population. We call that a random sample. But there are other methods. So a random sample is not the only way to collect your sample from your population. There are other ways. But in most of my work here, I'll be focusing on the random sample. Now, how can we violate that? Well, the sample only includes women of a specific racial or ethnic background. So that could mean that we didn't choose people randomly. It could mean there's some sense of self-selection there, or our sampling methods are biased in some way. I mean, not biased in a discriminatory sense, but biased in how we select people. Only women on LinkedIn are surveyed. Well, so we contact people on women on LinkedIn, and we ask them how tall they are. I don't know why we would do that. But my point here is that if we only ask women on LinkedIn, Well, the membership on LinkedIn is not representative of the broader population. Okay, and we should probably know that intuitively. It's people that work in industry and business and students and stuff like that, but that is not representative of the broad population. So it's not really random. And in like telephone surveys, this has been a common one over the years as people have moved entirely to cell phones, like me. Sometimes political pollsters will only call landlines. Well, that's not representative of the whole population either, because people who are young, I'm not that young, but I'm relatively young, a lot of them have gone strictly to cell phones. So if you just call landlines, you're not going to get a representative or totally random sample of the population. You're going to get a random sample of people with landlines, but that's not a random sample of all voters. So these are just some guidelines and ways in which selecting your sample in the wrong way can violate those guidelines. So when you're thinking about problems in class, or you're thinking about getting consumer information for your business, you have to keep in mind these sort of sampling guidelines when you do whatever work you're doing in class or in your business. Okay, let's change gears here for a few minutes and talk about the actual way in which the population and sample work when we're actually doing the work of statistical analysis. Now in this chart, we have population and sample in columns. And on the left-hand side, I have different sort of characteristics of the two. Now let's look at the idea of a measurement characteristic. Whenever we take a measurement of a population, we call that a parameter. So any sort of measurement characteristic about a population is called a parameter, a population parameter. When we take a measurement about a sample, we call that a statistic. Okay, so a sample statistic. So if you're reading something in your schoolwork, or you're reading some other business research or whatever else it might be, parameter, if you see it in the text, refers to the population. A statistic refers to the actual sample from a population. Okay, let's look at the mean. Now the population mean is denoted by the Greek letter mu. It kind of looks like a U with a little long tail on the left. Now, if you're in a statistics class for the first time, please, please, do not say moo, like a cow. It's not moo. I've heard it before from students and people in my own classes when they say moo is 5.8, and it sounds like a bunch of cows in the room. It's mu, M-U, okay? All right, there's my little soapbox moment. Now, the mean for a sample is an X with a bar across the top. We call it X bar. So in your work, if you're doing statistics or reading something, whenever you see mu, that's referring to the population mean. X bar is the sample mean. Okay, let's talk about variance. For the population, it's the Greek letter sigma, which kind of looks like an O with a little flare on the top. So sigma squared is the variance of the population. Sigma squared. Now for the sample, it can usually be shown two different ways. Sometimes it's shown as an S squared, or sometimes it's sigma squared sub X bar. Now that's a lot of words to just say, well, it's the variance, but it's the variance of the sample. And the way we know that is because it has an X bar below it. So it looks just like the sigma squared for the population, but it has an X bar down there to the lower right. It depends on the book you have and things like that. It goes both ways. All right, so standard deviation. Population standard deviation is just sigma. Now, if you remember my other video, the standard deviation is just the square root of the variance. So the square root of sigma squared is just sigma. Now for the sample standard deviation, it'll just be S, okay, because the square root of S squared is just S, or it can be sigma X bar, which is just the square root of sigma squared X bar. So depending on what you're reading and what you're working on, you might see it a couple different ways. The important thing, the reason I put this in here, is one, so you can understand your work better, and you can somewhat sound more credible when you're talking with your classmates and with your teacher, your business colleagues, or whatever else, if they feel that that's important. And in the end, it's just really good to understand the correct way these things are used in your work. So these are the way that population and sample are differentiated in different common characteristics and measurements. Now, because of that, you're going to see some formula differences. Now, when I mean formula differences, I mean formulas that are actually doing the same thing. So you will often see two versions of formulas, one for a population and one for a sample. This is probably the most important concept to get across from this video, and that is that a sample is always an approximation of the population. A sample is always an approximation of the population. So if I want to know the average number of hours spent online by children ages 11 to 17, if I go out and survey, or I determine how many hours they spend online during a week. Now, let's say I ask 100 young people how much time they spend online during the week. That 100 subjects in my study is only an approximation of all 11 to 17-year-olds online time. Always an approximation. Therefore, sample data sets always have error built into them, some uncertainty. So if I asked 100 of those young people about their online time, how do I know that's representative of all people that age? If I find out the educational attainment of 50 frequent Starbucks customers, how do I know that that's representative of all frequent Starbucks customers? I don't. Okay, there's some uncertainty in that sample. So you always have to keep that uncertainty in mind. It's extremely fundamental to our understanding of statistics. So is this sample a good approximation of the population we're interested in? Now, due to this uncertainty of the sample as compared to the population, we oftentimes have two formulas. Now, here's a formula difference example. If you're not used to the Greek letters and stuff, one, get used to them, because they're not really that difficult. And once you get the habit of it or the hang of it, they aren't that hard to understand. Let's look at the top one. First, we have sigma. Okay, well, remember from our nomenclature slide, what is sigma? Well, remember, it's the population standard deviation. Now look below that, we have just S. So what's S? Well, that's the sample standard deviation, right? So we have population and sample standard deviations. Now, look at the formulas themselves. Look for the differences. The square root is the same. We have the big sigma in there, which just means sum. We have x minus, well, on the top one we have x minus mu. On the bottom one we have x minus x bar. Well, why is that? Well, mu is the population mean. So it's going to be in our population formula. And then down below, we have x minus x bar. And why is that? Well, x bar is our sample mean. Now, what else is different? On top, we have divided by n, which is the number of measurements in our population. Now look below, we have n minus 1. And that's the number of samples we have in our sample. So if I sample 50 women for their height, that would be 50 minus 1. Almost the exact same formula. So what are the differences? Well, we have mu on the top versus x bar on the bottom. We have n on top versus n minus 1 on the bottom. But structurally, these formulas are the same. Okay, they're basically doing the same thing. But because one is the sample and one is the population, there are subtle differences even when they're measuring the same thing. Now the n minus 1 on the bottom of the sample standard deviation just indicates that we're estimating a parameter in our population. Okay, and I don't want to go into the whole spiel about the n minus 1 on the bottom, but just remember, all samples are an approximation. So in a way, this is not the technical term, but the samples have to be a little bit more lenient. They have to have a little bit more wiggle room. So their distributions are going to be a bit wider than our population. And that's the more specific way of putting it. That's not really important to this slide. What I was trying to get across to you is that because of the population and sample differences, you're going to see formulas that look very alike, but one is population and one is sample because of the differences and the uncertainty in our samples. All right, so we're just about done with this video. So, how many bulbs out of the 20,000 should halogen randomly sample in order to obtain an accurate estimate of the entire production run, which is the population? They're going to take a sample of bulbs to test. Question is, how many? And of course, we're not going to talk about it in this video. We're going to talk about that. We're going to talk about sample size and standard error in our next video. All right, so that's the basic concept of population data and sample data, how each one is unique, the characteristics they share, and how they are related when we're actually performing statistics on our data. Again, thank you very much for watching. Look forward to seeing you again next time.